than Chem 1 in that Chem 1 builds on itself a lot. You know, stuff that you used in Unit 1, I think you used in all the other units in Chem 1. But Chem 2 is a little more modularized. So it's almost like Monty Python says, now for something completely different. So we're kind of on to something different. It's more of a these are more of standalone topics. Except for, I guess, units 3 and 4 are kind of related. But one of the things in this class that students taking general chemistry all throughout the country, all throughout the world, I don't know, it's interesting, our daughter's taking Iowa State, and like they do the same stuff. So you in general chemistry need to understand a little bit about reaction rates. We're going to build up to this kind of understand behind the scenes what we call reaction kinetics. We're going to build up to that. But reaction kinetics, or I guess I should say reaction kinetics. Reaction kinetics are just like how fast something happens, like kinetic energy. Okay. So kinetics, kind of what's happening behind the scenes, the pathways happening behind the scenes. So why does it go so fast or why does it go so slow? Well, before we can kind of talk about why it goes so fast or why it goes so slow, we need to talk about how do you gauge the speed of a reaction? How do you gauge reaction rates? Well, if we kind of generally take reactants going to form products from left to right, reaction rate then would be the change in concentration per time. We're going to see that here in a minute, change in concentration per given amount of time. We can track either the reactants or the products. But you figure, from what we know, just logically, our reactants are going to get less, and our products are going to build up. So we kind of have this sort of thing going on. We can track either one to come up with the rate of the reaction. So the reactants will decrease and the products will increase. So we've talked about this proportionality symbol, and it has an inversely proportional relationship. What does that mean? Well, that means as you let time tick on, as time increases, rates actually will decrease. Okay? Put another, so that we have this inverse relationship. What does it mean when time increases, rate decreases? Well, rate decreasing means it just slows down. The reaction rate just slows down. It just does. They all do. Okay? So that's kind of interesting. First off, reactions don't happen right away, and then over time they'll go slower and slower. We'll kind of explain why that would be. It kind of makes sense once you see it. So how are we going to track the reaction rate? So we're going to let the letter R represent reactants and the letter P represent products. And what we can do this in the lab, is we can, for a given time, come up with, now here's something new. I think this is new. But if it's not new, anytime you see the brackets, that means molarity. Okay, so the molarity or the molar concentration of. So at a given snapshot time, we could say, what's the molar concentration of these things? So, and actually you're going to see this on a graph here in a minute. So at time 0, before you mix the reactants, or before you let the reactant, if it's something decomposing before it starts, okay. So you're at 0.2 moles per liter here, no product. 5 seconds in, you've got some of your reactant has decomposed. Okay, you can do the math there to see how much is decomposed, and some of your product is formed. Okay, 10 seconds in, okay, 15 seconds in, 20 seconds in. So these are like snapshots. What are the molar concentration as your product goes down, or as your reactant goes down and your product goes up? Makes sense. So this is maybe what that data would look like. We had through 20 seconds, this is like 30 seconds. But the red line is your reactant decreasing. These are molar concentrations. And this is time along the x-axis, molar concentration on the y-axis. And the green is your product increasing. And some of you may already have a sense for this, but I think my slides do this. So for instance, how do I say this? reaction rate is going to be the change, that's the delta, change in molar concentration of either the reactant or the product. We're kind of focusing on reactants over change in time. Now, as I have plotted that, here I have molar concentration of the reactant, and I have time. Does this make sense that actually this slope is change in y, change in x? That is change in molar concentration reactant, change in time. So the slope is an indication of the rate. So here we go. We could do it between 0 and looks like 2 seconds. We could do it between 2 and, that'd be 4 and 6 seconds, right? We could do it between 10 and 12 seconds. And I don't know, it's a subtle thing, but check out the slope. It's nice and, it's got a lot of horizontal, vertical here, and it's kind of flattening out. So my rate is changing. The slope of that line is changing. Okay, wow, it really slows down. Or, and sometimes this is what we do, we can say for the first 10 seconds, I can go ahead and get a slope of that. Okay, you're going to get different slopes, different rates, depending upon kind of how you grab your data. We could go from the initial to the final. But some of you guys kind of know how this works. Like if you have a curve like this, it's like a kind of got an exponential sort of probably equation running it. If I take a line tangent to the curve, that's the slope at that point. That's probably the coolest way to do it. So a line tangent to this curve would be kind of the best way I could describe the at 10 seconds what my rate is. So we'll it's kind of what we're talking about. So this is actually kind of showing you the decomposition of H2O2's hydrogen peroxide. And we see a slope tangent to the line up here, a line tangent to the curve. That's right, the line tangent to the curve, the slope of that line would be the rate. You kind of see the rate slowing down here, a line tangent to the curve. So as reactions go on, as time increases, rate decreases. Inverse relationship. Okay. So again, we can follow either one, the reactant or the products. So I kind of wrote up here the reaction rate. Rates are change in remember that's molar concentration of reactant per change in time. So these 1s and 2s here is just any time segment, because we're not going to get graphical analysis out necessarily and try to draw a line tangent to a point on the curve. So we're just going to grab 2 points and do our best to come up with a rate. But we could travel the decrease in reactants or the increase in products. Okay. Now, I said this is rate, but actually I'm going to have to kind of I'm going to have to kind of step back here. It is rate, but actually this is the rate of change of R, and this is the rate of change of P. And here in a minute, I'm going to have to tell you, regardless of whatever species you're following in a reaction, you only have one reaction rate. So I'm going to fix that in a minute. All right. So let's pick on, I think this actually picks on the data you had a few slides ago, where you were given every 5 seconds. Came up with the molar concentrations of the reactants, the products. Yeah, it is. Yeah. So see how that is, on page 1. You can kind of flip back and forth. But if we pick on the time 0 and the time 5 seconds, we could go ahead and knock out a rate over that interval. So it would be the change in the molar concentration, Are we okay with where that came from? And it's always final minus initial. So the final was 0.121 molar. The initial was 0.200 molar. Because we're going to get negative number there, right? And it is negative. So the change in the mole concentration of R over that time interval, you're looking at negative 0.079 moles per liter. The change in time would be final minus initial, 5 seconds minus 0 seconds, so you're looking at 5 seconds. So then all we got to do is take one last division. And so the rate of change of R, over that time interval is the negative 0.079. If you want to, sometimes I take these moles per liter and I just put a big M. Negative 0.079 moles per liter per second. And so then divide it out, and we end up, I guess it's probably better to leave it as moles per liter, because that will help us down the road. But you end up with the rate of change of R over that time interval, first 5 seconds, is negative 0.016 moles per liter per second. And does this make sense that since our reactants are going down, it should be negative, and your products are going up? We could do the math for that same from the 0 to 5 seconds for looking at the product form, and we would come up with the same absolute value of, so it would be 0.016 moles per liter per second, but it would be positive. And that's not always the case. Actually, that's only the case if your stoichiometry is a 1-to-1 like it is here. We're going to have to introduce the effect of stoichiometry coming up. So let's kind of, this is what we just did, 0 to 5 seconds, and we could do the same thing, 5 to 10, and 10 to 15, and 15 to 20. But I did it for you. Let's see if we find the increasing time, decreasing rates. Okay, I'm seeing a decrease in reaction rates with regard to the formation of the product and with regard to the conversion of the reactants. Okay. Well, that's good. We can get these numbers the same way we've got the other numbers. So like I said, the reaction rate, the formation of the product is equal to the consumption of the reactant only if your stoichiometry is 1-to-1, and it is here. I'm talking 100 miles an hour again. So the rate of the formation of products will always be positive, okay? And the rate of the, and also, I call it the rate. Okay, so I have the change in concentration of the reactants. Okay, those rates, but then I have the reported rate. And it's always going to be positive. So here we go. Well, how would we go about this sort of thing? We have one reactant, A. Notice that 2, 2, and 1 are the stoichiometric coefficients in front of the A and the B and the C. And we have two products, B and C are formed. Well, we could go ahead and track the rate of change of A. We could track the rate of change of B. We could track the rate of change of C. But we can only report one rate. So we'll have one, the rate, and then we'll have these three different rates. So, for instance, like this says, for every 2 moles of A that are consumed, 1 mole of C will be formed. So it makes a difference which one you're tracking. Maybe different number. So I'm just going to throw some numbers out there at you. So anytime you see the brackets are molar concentrations of, and this little 0 means initial. So this is the initial molar concentration rate times 0. Right? After 25 seconds, notice that A is a reactant and A has decreased to 0.060 moles per liter. And I actually kind of move this because you're going to have to be able to think this through.
see, I've never done this like this, but start, end. So for instance, I started with 0.100 moles per liter. I ended with 0.060 moles per liter. And actually, I can come up with a remaining if I need to. But then the other one over here, we're going to kind of compare it to C, I think. I started with 0.000 moles per liter. And we need to be able to do stoichiometry. Oh, yeah. Remaining. I'm going to change this to used. Do you see where the amount used was 0.040 moles per liter? Does this make sense that the amount used or converted or whatever, actually I can use stoichiometry to come up with the moles of that was formed?
If I used 0.040 moles per liter and I converted it to products, that must mean I must have formed
Does this make sense? 0.020 moles per liter of C. And I got math to show you that. I'm just bird's eye view. Does that make sense?
It does to me. And that's going to be important, that little bit of stoichiometry. So let's see what that looks like, kind of doing it the right way. So we're going to use these A values, the change in molar concentration of A, to come up with a delta A. Change in time, of course, is 25 seconds. And then we're going to use this sort of information to come up with the change in molar concentration of C. Change in time is also 25 seconds. So we're going to come up with the rate of change of A and rate of change of C. So the rate of change of A is like this. It's final minus initial. So the final was 0.060 moles per liter. The initial was 0.100 moles per liter. And the change in time was 25 seconds. So if I take negative 0.040 moles per liter divided by 25.0 seconds, rounded it to 2 sig figs, you're looking at a rate of change of A as negative 0.0016 moles per liter per second. Rate of change of A. And the way we show rate of change of A is like you see it up there. Change in molar concentration of A, change in time. All right. So let's look at C. And it's kind of like I told you before. We can deduce how much of C was formed over that 25 seconds based upon stoichiometry. We know that 0.040 moles of A reacted and was converted to B and C. We can use simple stoichiometry of a 1 mole of C over 2 moles of A from the stoichiometric coefficients. And then this is where that number I just kind of jotted down a minute ago came from, or how we get it doing it the right way. So we know over the same time interval, the moles per liter of C formed must have only been 0.020 moles per liter. Now we have a molar concentration of C at 25 seconds. Of course, the molar concentration of C at time 0 is 0. So now we have something to come up with our delta molar concentration C's. So our change in molar over the same time interval, change in molar concentration of C by a change in time. And just so we're on the same page, I think this would have been, I would have been better served if I recognized that that is actually
It's final minus initial, so the final was 2 point, oh goodness, wait, pen doesn't want to work. The final was 0.020 minus 0.000. Okay, that's where that number came from. Time interval 25 seconds. So when I divide that out, I get the change in molar concentration of C, or the rate of change of C. Rate of change of C is positive because it's a product, and it's 0.0008 moles per liter per second. Okay. So it's the same reaction, but we have these differences in what you track. But I said there needs to be one real rate of change, and that will be positive. So, hold that thought. If we compare the absolute value of these rates of change, we recognize that this one is twice as much, right? Negative, but absolute value is twice as much. So actually, the way we handle kind of removing the effect of the stoichiometric coefficient is that we're going to take our rates and we're going to divide them by the stoichiometric coefficient, or multiply them by 1 over the stoichiometric coefficient. So by convention, the rate of change of a reaction, not the tracking of reactant or product, is reported as always positive, and we remove if what we're tracking has a stoichiometric coefficient of anything other than 1, then we can think of it as two ways. We can either, I'll just go ahead and show you what I like to do. I like to multiply it by 1 over the stoichiometric coefficient. 1 over the stoichiometric coefficient. Stoichiometric coefficient here, 1. Coefficient here is 2. And it's a divide by the same. All right. So we could kind of summarize then. Notice what this slide says is if I want to know the real rate, I actually would have to go ahead and take the rate of change of A. Since it's a reactant, I would have to take it times -1. And since it's got a stoichiometric coefficient of 2, I would have to divide by 2, multiply by 1/2. So B, we have to, it's positive, so we don't have to take it times -1 because it's a product being formed, but we have to divide by 2. And C, since it's a product, we don't have to multiply by -1. Since the stoichiometric coefficient is 1, we don't have to divide by 8. So that would be the rate. So there's a difference between the rate of change of a reactant product versus the rate. Sometimes it's okay, very good. So the next part, so you'll have some problems when you get to kind of do that sort of thinking through coming up with some reaction rates. But this is actually getting into kind of like the reaction mechanisms. Why does a reaction occur at all? And what takes it so long? I mean, to me, you have to understand why it occurs, and that's related to why it takes it so long. So first off, and after I kind of, you see some of these videos, you're like, it's surprising anything ever gets done. So if you have two reactants, they must find each other and collide. Not only do they need to find each other and collide, but they need to have enough energy. Sometimes we're going to talk about energy barriers. They need to have enough energy to, we say, proceed from reactants to products. Not only that, but the third factor is, they find each other and they have sufficient energy, but they're not lined up right. Then it's okay? It's like surprising anything gets done. So we'll be talking more about these three factors, and I've got some videos to kind of show you. These all have to do with how fast a reaction will occur.
or will it occur at all. So I've got some videos to kind of show you how this works. We'll be talking more about these as we talk about reaction rates. But let's see. Well, let's check out these videos. Okay. This is showing an orientation issue. Notice the difference between the first one and the second one is that the carbon monoxide is turned around. And I'll just go ahead and cut to the chase a little bit that catalysts is the word I was trying to think of. Catalysts are great at like providing the correct orientation. So why does a reaction occur at a certain rate? And those were all things that all three factors go into how fast a reaction will occur. Well, it depends on, you figure if your reactants aren't present in very concentrated amounts, they're not going to find each other. Temperature, well, that's an activation energy problem. Surface area, again, finding the reactants finding each other. And I mentioned catalyst is actually an orientation issue. Now, this will make more sense, the term reaction orders. So you just kind of stick this in the, we're going to talk about reaction orders next week. But if your reaction orders are positive, and the ones what we talked about are, then as you increase concentration, then it'll go faster. Increased concentration will go faster. Well, does that make sense then why the reaction rates slow down as your reactants go away? Less and less. Decreasing concentration, it's a moving target. Increase the temperature, and of the three factors we talked about, we'll kind of go into the mathematical bit about behind the scenes, but as you increase temperature, you have more energy. So maybe you have more molecules that have the right enough sufficient energy to overcome the activation barrier. I had to double check and look this up because every semester I show this and I'm like, heterogeneous phase reactions. All that is you have two reactants, 2, 3, 4 reactants. Just two reactants, and they're in different physical phases. So you might have a gas and a solid, or a solid and a liquid, or something like that. But for those sort of reactions where we have two reactants in different physical phases, surface area is important, and it can actually help your reactant particles find each other. Yes. Catalyst, again, it actually will allow for the orientation factor to be more successful. And the cool thing about a catalyst is it's optional in that the reaction will occur without it, but it will always occur faster with a catalyst. So let's check out these videos. Left one is dilute HCl, and wait a minute. It's not the HCl. They're talking, this one is ground up iron, and this one is iron in a nail. So the HCl is the same in both, but you see greater reactivity here because of the surface area, the chopped up iron versus iron. This is sad. This is like I'm sure, historic monument, but you figure entropy is all around us, and so there is a decay of marble stones. But this says that pollution, like specifically with sulfur dioxide, can accelerate its decomposition. Sad. That's a sad. Catalysts actually work. They're not consumed. What they do is provide an alternate pathway for your reactants to proceed to form products. So what you're seeing is time, kind of think of time along the x-axis. Think of energy barrier along the y-axis. And can you see where the red one, the red curve without a catalyst, has that much energy to overcome it? An alternate pathway providing orientation, proper orientation, The blue one is if you add a catalyst, so the energy barrier is less. It provides an alternate mechanism.
So the greater the energy barrier, the harder it is.
Exactly. The greater the energy, the harder it is. Yeah.
So that's why there's like a sudden drop. The blue one is like.
It's got an additional component there that's just helping facilitate the reaction. Yeah. And
So the catalyst is only one purpose.
so the catalyst is the whole blue line. Yeah.
Like the bump is like really vigorous, right? Like the reaction happening
The bump
quickly.
would be
Like going down.
the bump would.
let's see. How do I say this? I think we're all on the same page here. So this would be, and we're going to actually talk about energy barriers. So to overcome, this is got two energy barriers, but they're lower than this one. And this isn't time, this is the extent of the reaction, because you would figure kind of maybe like you said, Daniel, the fact this blue one that has a catalyst, it has a lower energy barrier, and so it will actually occur faster. We're talking about reaction
I
rates.
guess my question was, what's with the dip in it too?
What's with the dip, the two dips? That goes to kind of what's going on behind the scenes. The fact that it has two dips means that there are two steps in its reaction mechanism behind the steps versus the one step, which requires more energy. Good for you. And that's it, Mom. Hope I didn't talk too fast.
Actually, that makes a lot of sense.
Good. That's what we're after.
So this will be due on Monday. And we don't have class next Friday. Teacher in service.
So we home.
That's
So, do you still have here all the fruits that you brought yesterday? Because I'm sorry.
Oh no, I took it home. I took it home.
That's alright. I'm just gonna
That cookie was like the best.
Oh, you should have seen Benny during test, man. She ate lots of those.
cookies.
Yeah.